Hello, I'm Ugo Battiston. I'm a PhD student under the supervision of Philippe Claus and Marc Perrache, and I work in the INRIA CAMU team in the eCube laboratory at Strasbourg. And I will show you how to connect Kokkos with the Polyhedral Model. So firstly, I will present Kokkos Polyhedral Model, an automatic tool to apply the Polyhedral Model. And after, I will explain how to bridge Kokkos with Poly, with also a complex case. And after, I will talk about scheduler and automatic correctness verification. And after, I will present result and also future work. So, Kokkos is a modern library, is a modern C++ template library. It allows the abstraction of parallelism, and it provides performance portability across different architecture, so like CPU and GPU. So an example, but I think I will skip it. And my work is the goal of my work is improve performance, Kokkos performance. And if we see inside the library, the parallel 4, we can see a regular loop structure with a well-defined loop bound and the Kokkos view with a affine library access pattern. And this is a perfect structure to apply the Polyhedral model. So, what is the Polyhedral model? The Polyhedral model is a geometrical representation of loops with an integer point in the polyhedron. So on the top right, you can see a code with a E loop and a G loop, and this can be represented as a green rectangle below, and each red point represents one interaction. So now we have a geometrical object, and we can apply geometrical transformation, and after we can translate it directly in a program transformation. And the Polyhedral model can enable some loop optimization, like reorganization of instruction, improve cache locality, enable vectorization, also transformation like tiling or skewing, and also expose parallelism opportunity. So a real example with this stencil. On the top, we have a stencil, a basic stencil with E dependence on the. We have a dependence on the previous E iteration and the previous G iteration. So we can parallelize E or G, but with a basic skewing transformation, we can obtain the blue iteration domain, and we can parallelize the second G loop. So this is magical, but this is mathematical, and we want create automatic tool to write this and to write this because it's very hard to write and to read for a human, and this is why we use automatic polyhedral tool. So I will present Poly because I will use it. Poly is a LLVM subproject directly usable from Clang, and Poly have an advantage because it directly analyze the LLVM intermediate representation rather than the source code, and it's allowed to abstract the C++ complexity because in IR we don't have a template or a metaprogramming. And now I will present how to connect really Kokkos with Poly. Okay, firstly we need make some modification in Kokkos. The first, we need to do the isolation of loops and also remove the automatic tailing because we want the cleanest code possible to make easily the detection of scope. A scope is a static control part, is a region of code who can apply the Polyhedral model. And we also need add useful information for the Polyhedral model, so array dimension, array pointer, or delinearized iterators and also the used backend with annotation. And an example of a useful annotation is array, because the Polyhedral model needs affine access of array. So like E and G, but the compiler vision of array is linearized shape. At the bottom of the slide, you can see a dot data E multiply with M plus G, and we want find E and G. But for this, we need apply the delinearization pass. So this is a retro engineering pass to get affine access in a multidimensional. So we need to get term. Term is in this case M or N, but in some case term can be opaque, because we access the matrix with zero value, and we lost this information. And with annotation, we can get strong delinearization. Another modification is in poly. Some array pointers or array dimension can be loaded inside the loop, because the compiler cannot understand that invariant information. And with annotation, we can say this is array pointer or array dimension, and we can move load outside the loop. And we outside loops. So we have made some modification in Kokkos, but we want to give the possibility to the user to choose to enable or disable the Polyhedral analysis. And this is why I created a new use polyhedral option to allow the user to say, yes, we will use the Polyhedral analysis or no. So now at this step we can apply the Polyhedral model on a basic example, but we can get a complex case, and I will present you some. Okay. An issue is when the user write multiple parallel for to write one kernel. This gives a limited view of kernel for the compiler and also for the Polyhedral model, and this is why we want global vision of kernel with one parallel for. And this is why I propose this implementation. So line 6, you can see parallel for with multiple kernels. So here we have two kernels with two pair of policy and kernels. But we have an issue, because the first kernel use TMP and the second use also TMP. But in IR, we have two distinct pointers to describe one value. But for the Polyhedral model, we need write memory access, so we need one TMP access. So not one TMP access, but one TMP parameter. But to solve this, I changed the view definition to add string literal directly in type. And now we can say the view A, for example, is a view TMP have two different types. And when we analyze the IR, we can see the type of the first TMP in the first kernel and the first TMP in the second kernel are the same, and we can fuse the usage in one. So now we have a good array access, but we have also an issue with the loop bound parameters, because, for example, in the first policy we use ny, and also in the second ny, But in IR, we have two different values to define this. And we also need to fuse this usage in one. And this is why after the polyopt option, I have added an assumption string with a grammar to say the first policy at the index 0, so the first policy, upper 0, so the first upper bound, is equal to the second policy at the index 1, upper 0. And now we have only one ny only one ny upper bound, and we can apply the polyhedral model. So, but we have also an issue in IR because each Kokkos lambda function, each Kokkos lambda come with a preheader to load array or array dimension or data, and at the left, you can see in between loop A and loop B, we have a preheader B, and this breaks the detection because every parameter of the scope need to be loaded before, and this is why we need to reorganize block to make to do the preheader before loops, and now we can detect scope with the A and B inside the one scope. So I will talk about assumption. Assumption was created for global vision, but is also useful for one kernel. For example, in this kernel, the parameter represents the E loop with the N upper bound, and inside the kernel we have a C++ loop with a N bound, and in IR we see two different variables, and with the assumption string we can say the second the policy 0 upper bound 0 equal to the n, because we have marked upper bound n inside the kernel with a Kokkos macro Kokkos loop bound. And also I put an example of other assumption with inequality. It's possible. So another complex case is triangular loops, because the right code, you can see parallel for on E, and inside you have parallel a loop for G with E in loop bound condition. So for the first iteration of E, the loop G does not exist, and in the control flow graph, you can see at the left, the statement one have a comparison instruction to say if we have if we are in the first iteration, go to the statement 3, and else go to the statement 2. And this breaks the scope detection, because array access are not affine, because it's depend of condition of inside loop condition. So to solve this, we need to apply loop peeling. This is a LLVM transformation to extract n iteration of loop. So here we extract the first iteration. In the red rectangle, you have you can see the first iteration, so the statement 1 and statement 3. And after, in the purple rectangle, you have the n-1 iteration. But here we don't have the comparison instruction, because in this rectangle, the loop J exists for all iterations. So now I will talk about scheduler. So the default scheduler of Poly is ESL, and this is good, but it's not the best. And this is why I have added the Pluto scheduler in Poly. So we generate the polyhedral representation suitable for Pluto, And after we apply Pluto transformation on this, and after we inject it directly in Poly. And this is useful because Pluto use different heuristic and also apply other transformation like diamond tiling that the scheduler ISL cannot do. And this is perfect, for example, for stencil. And another second work is an automatic correctness verification. So when a user writes a kernel Kokkos, he can parallelize the outermost loop, and the Polyhedral model can say which loop with the schedule can be parallel. And before the schedule optimization, we can say if the outermost loops aren't parallel, so the user make a mistake in the kernel. And we have a mathematical certification of this issue. So now I will present you some results. So I use the Polybench suite. This is a benchmark suite with many kernels, with stencil, BLAS, solver, image computing, with a dual AMD EPIC with 32 cores, so 64 cores. And I compare the Kokkos version with the Kokkos with the Poly version in parallel. And we obtained a massive speedup on many kernels. Only 3 have a slowdown, and ADI have a issue because the code as marked as parallel, but in real is not parallel, is sequential. And for a little summary on the Polybench, Polybench is 30 kernels. I tested 18. 13 show a speed up, 3 show a slowdown, and 2 benchmark doesn't work because the runtime condition to use the Polyhedral version doesn't work or just a crash. 6 kernel with a triangular loop on initialization. I show triangular loops with the iterator in conditions because I use LLVM 19, and in this version we can do peeling back, so we can extract last iteration of a loop, but it's future work. 1 kernel with a bad scope detection, 2 kernel without parallelism, but I will benchmark this, and 3 kernel with a conditional control follow loop, and the Polyhedral model cannot be transformed this. And for my future work, fix Poly benchmark suite, the last kernels, and also make other benchmark like a real case benchmark. And we have also an issue because Kokkos can generate GPU code, but Poly cannot. And this is why we want to use the PPCG schedule to generate a scheduler for a schedule for GPU, and after we inject it directly in Poly to generate LLVM GPU IR. Finish. Thank you.
Thank you very much, Ugo. This was a great and very interesting presentation. So we have time for some questions. I don't know if there are questions in the audience. Well, I do have one. So in your example, you provide some constraints that can then be used for the scheduling through a string.
Yes.
I was wondering if some of those constraints could be automatically extracted or taken from the specific case of Kokkos to inject them automatically in the polyhedral model.
Yes, I think it's possible. Here, I miss some assumption because in Kokkos, lower bound, constant bound are defined by parameter and not constant. And for test, I need put in the string quality zero, lower zero is zero, etc. But I think with the deep analysis of code, I think we can get this information, but
Okay.
it's not implemented.
Mhm. I see. We have a question in the chat. Harry is asking if you can re-explain the three cases that showed a slowdown.
Durbin, I don't know why, and it's really no, I don't know. I did, I need to investigate, but ID the code run in sequential, but is marked as parallel, but I don't know why. I did this benchmark 2 days, so I don't have time to investigate.
And can you maybe say a bit more about what those three codes look like?
What?
What kind of pattern do they implement? So, for example, Derbin, what is the code? Do you have any idea? Is that like nested loop, a single loop? What does it
Uh,
look like?
I can show you directly.
Mhm.
You have stencil, so this is a code doesn't work.
Can you
You have
increase the size a little or reduce the
oh
size
yes,
of the?
sorry.
Yeah, great. Thank you.
You have a more basic kernel like Jacobi. Here we have you can see the vanilla version. It's,
And so the three versions that had issues were ADI, Hit 3D,
it's
and
3D is here.
so I guess Hit 3D is a 3D stencil.
Yes, it's 3D stencil.
Mhm.
You have also linear algebra
ADI,
like
what does it
ADI.
look like, ADI?
ADI. It's like this in oh, in vanilla C.
Okay, so this is linear algebra, I guess.
You have also Glass, Gem, Gemware, Cir2K also.
Mhm.
Kernel like 2mm or 3mm. This is a 3 multiplication
Mhm.
like this.
But this behaved well, right? In your
What?
case. These ones, they were going faster with your improvement. The one that were misbehaving were ADI, Hit 3D, and there was a third one that was
Durbin.
Durbin.
Oh yes, Durbin is.
Okay, I don't know if that answers your question, Harry.
but it was useful to see. Thanks.
Are there any other questions? On my side, I was also wondering, so the work you've done now is mostly on the CPU side, and in the end,
Yes.
you were saying you're gonna explore GPU next. Do you expect? I mean, this is kind of an open question, but do you expect there is as much you can gain on GPU with scheduling? Because I mean, GPU, it seems like you have so many independent threads in the end, you don't do much scheduling. So what can you
I
gain on
don't
GPU?
I don't know. My thesis director have made some tests. It better, but I don't know
Okay.
the impact.
So you already have some examples where you can improve the situation.
Yes.
Okay, very interesting. Anyone else?
Yeah, I was gonna ask um, if you're looking at some blast kernels, I'd be interested at some point into having a look at how you implement them and how you eventually get your speed up. I'm in charge of the math libraries for the Kokkos ecosystem, so that's kind of a topic that's close to my
For
interest.
example, gem is implement like this with the external parameter.
Yeah, but Gem is really sensitive on CPU to the sizes you're using when you do panel updates. So for example, here I see the inner nested loop is a AIK times PKJ. Yes, you're looping over J, you're looping over K. And
By
typically,
default, the K and G dimension are inverse.
what do you mean?
The for cache locality, the best order loops is KG.
Yeah, well,
It's
okay.
already do in kernel.
Okay, because the typically, yeah, you want to do the panel updates and then have these loops be sized, NJ and K specifically for the cache sizes that you have available on your CPUs. And so I mean, I'd be curious to see if this approach is, yeah, how much benefit you get out of it, because typically that's like a well-studied problem, and I don't know that there is a ton of, if there's new opportunities, it's exciting. I will say that because I thought it was very well studied and there was not a lot of performance left to be gained at this point. So yeah, all I'm saying is I'm kind of interested to see like how you get extra performance
Okay.
just because I didn't expect there was the too much, especially when you show like a 4 or 5x. It's somewhat
Yes.
surprising, but I'm suspecting it depends a little bit on how you compare things as well. So.
Maybe a question for the two of you, but so Hugo, what you do is, if I understand correctly, you take a naive implementation of gem, the most simple expression of the problem, and you let then the compiler do the optimization. But Luc, I guess and I imagine that in Kokkos kernel you have already implemented in the code some cache blocking, some stuff like that to improve the performance compared to the very naive implementation that we see here, or is that what the implementation in Kokkos kernel looks like?
So we have the implementation uh, is definitely optimized for performance. For example, I recall on GPU we spent a lot of time doing double caching strategies just to have like highest throughput possible and things like that. The only thing that we haven't done is we're not using Tensor Core intrinsic explicitly, so that's where we could gain like further performance. But on CPU, the idea is to, kind of follow, I think you probably know, I think, Flame is like a library developed in the University of Texas. And Bliss, sorry, actually, I was thinking of Bliss. And they had like a couple of papers on the anatomy of a gem on CPU, and they explained very clearly like the looping strategy. And I think it's kind of the standard at this point to implement this type of algorithms. So the nice thing is if you have only 3 loops and you manage to express all of that automatically for the compiler, it makes it easier for beginners to get like all the performance without having the knowledge of these research papers. And that's quite valuable. That's why I'm trying to like figure out exactly how that compares. And, because if that's the case, like, this will make a lot of application happy. They'll get more performance more easily.
Yeah, I guess you have kind of a Pareto optimal. You have a multiple objective optimization problem where you want the code to be as easy as possible to write and as performant as possible. And here you compare with similar complexity of writing the code, what kind of performance you can gain, Ugo. But maybe it would be interesting to compare that gem, for example, to what you have, for example, in Kokkos kernel, where you have experts that have hand optimized. So of course this is way more complex in terms of writing the code, but this is kind of the best performance you can achieve. So you can say, okay, by writing the code in the most naive way possible and the most straightforward way possible, I can reach that percentage of the top performance that hand optimized kernel can reach. That would be very interesting to see.
Yeah, and I think the blast kernels are the right ones to use for that because they have been under scrutiny, and the research has been done for many, many years. So I think we have at least pretty good implementation for this.
Yep. Thank you. Any other question or feedback? Well, if not, let's thank Ugo again for this great presentation and this great work. I hope we will see another presentation at the end of your PhD work with even more results. But in the meantime, let's thank you again. And our next Kokkos Tea time will happen as usual on the 3rd Wednesday of the month on the 21st of January. The same time, same place. The subject is not announced yet. If you want to talk in January, please let us know and send us a message. If you want to talk on another date, please let us know and send us a message. And see you in January. Bye-bye. Thank you, everyone. And thank you, Ugo.